There exists a boundary where the known laws of the universe simply stop. This is the event horizon of a black hole, a point of no return from which nothing, not even a beam of light, can ever come back. Today, we are going to do something unprecedented. We will cross that line together in your mind and analyze exactly what happens during the moment you cross the event horizon, second by agonizing second. By the end, you will possess a complete, visceral understanding of one of reality's most extreme phenomena, from the silent mathematical transition to the overwhelming sensory breakdown that follows. We will confront bizarre paradoxes, like watching the future of the cosmos flash before your eyes while being trapped forever, and grapple with what this means for the very nature of space and time. This journey will stretch your perception of reality to its absolute limit. What do you fear most about the idea of an inescapable fate? Think of a river flowing smoothly toward a waterfall. For most of its journey, the water moves with a gentle, predictable current. But as it nears the edge, that current becomes stronger, faster, and utterly inescapable. The event horizon is that waterfall's edge in the fabric of the universe. It is not a physical wall you could touch or crash into. It is a mathematical line drawn in the geometry of spacetime itself, defined by one simple, terrifying rule. At this precise boundary, the pull of gravity becomes so intense that the speed needed to escape it equals the speed of light. Since nothing in the universe can travel faster than light, nothing can ever come back out. Renowned physicist Kip Thorne aptly called it a one-way membrane. Information, matter, light, all of it can flow inward, but nothing, absolutely nothing, can ever be transmitted back outward. This creates a profound observational effect for anyone watching from a safe distance. As an object, say a probe or a doomed spacecraft, approaches this boundary, the light it emits struggles against the immense gravity. The light waves are stretched to longer, redder wavelengths in a process called gravitational redshift. To an outside observer, the object would appear to slow down, redden, and then fade from view, not with a flash, but with a slow, eerie dimming into nothingness. It is as if the object is being erased from the universe pixel by pixel, its final signal stretched into an infinite, silent sigh. This boundary, this silent and invisible point of no return, is our gateway. To cross it is to leave the known cosmos behind and enter a realm where the rules we rely on for reality begin to unravel one by one. Our astronaut is not yet falling. For now, they remain in a stable, if doomed, orbit, their spacecraft tracing elegant circles against the abyss. But this orbit is decaying, its energy slowly being sapped by the black hole's immense gravity. Think of a toy boat caught in a vast cosmic whirlpool. At first, the boat can circle the outer edges with ease, but with each rotation, the inward pull grows subtly stronger, dragging it imperceptibly closer to the central drain. This is the final, graceful dance before the plunge. In orbital mechanics, there exists a critical boundary known as the innermost stable circular orbit. This is the last possible path where an object can, in theory, maintain a stable loop around the black hole without requiring constant thrust to avoid falling in. For our astronaut, crossing inside this boundary is the point of terminal commitment. It is the moment the whirlpool's current finally overpowers the boat's ability to steer away. No engine, no matter how powerful, can now pull them back into a safe orbit. The fall becomes mathematically inevitable. Even in these final moments of relative stability, the black hole announces its presence in unsettling ways. The spacecraft, though still intact, begins to feel the difference in gravity between its nose and tail. This is the awakening of tidal forces. The pull on the side of the ship facing the black hole is minutely stronger than the pull on the side facing away. The entire craft experiences a gentle, persistent stretching force, as if it were a piece of taffy being slowly pulled apart lengthwise. From the astronaut's perspective inside, this might feel like a faint, constant tug in one direction, or it might simply register as a strange, persistent reading on the ship's structural integrity sensors. Meanwhile, for any hypothetical observers watching from a safe distance with a powerful telescope, a profound distortion is already taking place. Due to the extreme warping of spacetime, time itself is flowing at different rates. The astronaut's clock, from the outside viewer's perspective, is ticking slower and slower. A minute for the astronaut might be an hour, a day, or a year for those watching from afar. The astronaut is, in a very real sense, already beginning to separate from the shared timeline of the rest of the universe, slipping into a slower stream of time as they spiral inward. This approach phase is a masterclass in mounting tension. It is a slow, silent crescendo where the laws of physics themselves tighten like a noose, where stability is stripped away piece by piece, and where the only direction left is down. The innermost stable orbit is crossed, the engines fire one last futile correction, and then the last graceful arc of the spiral ends. The stable orbit decays into a trajectory with only one destination. The plunge begins. The spacecraft's hull intersects the invisible sphere, 0 seconds. This is the precise coordinate where the mathematical definition of outside the universe ends. In this single, silent instant, our astronaut crosses the event horizon. There is no shudder of impact, no warning siren, no flash of light to mark the occasion. Locally, inside the cockpit, it feels like absolutely nothing has changed. The laws of physics, as the astronaut experiences them, remain smooth and continuous. This is the profound, counterintuitive heart of the crossing. You do not feel the point of no return because it is not a physical barrier you crash through. It is a rearrangement of the geometry of the universe around you. Before this moment, your possible future paths through spacetime included trajectories that could, with enough thrust, curve back out into the cosmos. The moment your ship passes that mathematical line, the fabric of reality reconfigures. Every single possible path that lies ahead of you, every future the universe can now offer, bends inexorably inward toward the central singularity. Think of it like this: you are in a rowboat on a wide, calm river. As long as you are upstream of a massive waterfall, you can, with great effort, row against the current and reach the shore. But the moment the current carries you over the lip of the falls, your relationship with the river changes completely. No amount of rowing can bring you back up. All possible motions now lead downstream. The crossing of the event horizon is that lip, translated into the fundamental structure of spacetime itself. You have entered a prison where the walls are not made of matter but of destiny. The door, which felt like open space as you passed through, has silently sealed shut behind you forever. And the truly unsettling journey is only just beginning. But outside the cockpit window, the universe begins to rewrite itself. The first second inside the event horizon is a spectacle of cosmic distortion. That serene starfield you left behind does not simply vanish. Instead, the paths of all the light rays that followed you in are bent so severely by the black hole's gravity that they are now focused into a single, brilliant, and shrinking ring of light directly above you, often called the photon sphere. It is as if the entire history of the cosmos, every star and galaxy you ever knew, has been compressed and projected onto a circular screen that is now your sky. This ring is not static. It is collapsing inward, tightening like a noose made of pure starlight because you are still falling, plunging deeper into the abyss. Ahead of you, in the direction of your fall, there is only an impenetrable darkness. This is the visual proof of your new reality. The light from events happening in the outside universe after the moment you crossed can no longer reach you. You have fallen into a pit so deep that news of the present can never catch up. Yet you can still see the past. All the light that was emitted before your crossing is still raining down upon you, focused into that singular, dazzling ring. This creates a bizarre and haunting visual effect because you are catching up with light from increasingly ancient cosmic events. The universe you see in that ring appears to speed up. Stars might be born, live, and die in a blur. Galaxies might collide and merge in a silent, accelerated dance. You are watching a fast-forwarded history of everything that came before you, a final, breathtaking film reel of creation playing out on the walls of your prison, while the present and future of the cosmos remain forever dark and silent ahead. This gentle stretching is the first physical whisper of the abyss. The second inside the event horizon belongs not to light, but to force. The visual spectacle of the collapsing sky continues, but a new and undeniable sensation begins to register within the spacecraft and the astronaut's own body. This is the awakening of the tidal gradient, a phenomenon physicists describe with a vivid and unsettling term, spaghettification. The principle is simple, yet its implications are profound. Gravity's pull is not uniform. If our astronaut is falling feet first toward the singularity, the force on their feet is now measurably stronger than the force on their head. The difference is subtle at first, a faint, persistent tug along the length of the body, as if every molecule is being drawn downward with a slightly different urgency. It feels less like a sudden yank and more like the slow, steady pull on a piece of warm taffy, a lengthening that is initially manageable but utterly inexorable. This moment marks a critical shift in the journey. We move from a realm of observation and distorted light into the domain of direct, tangible physical experience. The black hole is no longer just a warper of space and time. It is now a sculptor of matter, and you are its medium. The scale of the black hole is what makes this process gradual rather than immediately catastrophic. For a small, stellar mass black hole, these tidal forces are so ferociously concentrated that spaghettification would have shredded an object long before it even reached the event horizon. But here, at the threshold of a supermassive giant, the gravity gradient is spread over such a vast distance that the stretching begins as a creeping, almost gentle inevitability. It is the difference between being snapped by a sudden, violent whip and being slowly drawn apart by a relentless cosmic tide. This is the universe applying its most fundamental pressure, not with explosive violence, but with the silent, geometric certainty of curved space. The seconds tick forward and a profound reorientation takes hold. The third, fourth, and fifth seconds inside the event horizon are defined by a single, overwhelming geometric truth. The very idea of direction is rewritten. In the normal universe, you have a full sphere of possibilities: forward, back, left, right, up, and down. Here, that sphere collapses into a line. All that remains is radial motion, a one-dimensional arrow pointing relentlessly toward the center. It is as if you are in an elevator in freefall, but with a terrifying twist. The moment the cables snap, not just the floor, but every surface, every wall, and even the ceiling you look up toward, all now conceptually represent the down direction. There is no sideways anymore, only a deeper plunge. Theoretically, inside your spacecraft, you could still move. You could push off a wall, float across the cabin, or reach for a control panel. But this local motion is an illusion of freedom. In the grand geometry of this place, any movement you make merely changes the angle of your spiral into the abyss. Pushing off the wall to your left doesn't take you left in any cosmic sense. It just adjusts the tightness of your corkscrew path toward the same singular destination. It is like trying to swim sideways in a river that is funneling into a massive drain. You might create a little circular current around yourself, but the river's ultimate flow sweeps you along regardless. Space itself is no longer a stage you move across. It is the current that carries you. The geometry you now inhabit is that of a collapsing funnel, where the walls of spacetime are not just around you, they are actively constricting, guiding every possible path inward. This absolute nature of the trajectory is the final mathematical confirmation of your fate. Every future you have is a variation on a theme of descent. These next seconds introduce a paradox that is deeply personal. For the astronaut, time continues its steady march. The ship's clock ticks from 6 to 10, each second measured with familiar precision by their own heartbeat and breath. But the view through the viewport tells a story of time gone mad. That brilliant ring of cosmic light above, the compressed sky of the entire external universe, is no longer a static painting. It has become a frenzied, high-speed film. Within those few seconds of personal experience, the astronaut witnesses stars in that ring flaring to life and burning out in brilliant supernova. They see galaxies spinning, colliding, and merging in a silent, hyper-accelerated ballet. What would it feel like to watch the future of everything you ever knew flash before your eyes, while being utterly and permanently severed from it? This is not a metaphor. It is the direct visual consequence of gravitational time dilation taken to its absolute extreme. From the perspective of the outside universe, time for the astronaut at the event horizon has slowed to a near standstill. But from the astronaut's own frame of reference, it is the universe's time that has wildly accelerated. With each meter they fall deeper into the gravity well. The light reaching them is from events further and further into the cosmic future. They are, in a very real sense, making a one-way leap through time, witnessing eons pass in moments. Yet this gift of foresight is the cruelest form of isolation. They are watching a history that is, for everyone else, yet to happen, a future they can observe but never touch, never influence, and never be a part of. The profound loneliness of this moment transcends physics. It is the realization that you are now a ghost to the cosmos, a spectator chained to the front row of a play that has already written you out of the script. The gentle tug becomes a persistent, undeniable pull. Between the 11th and 20th seconds, the environment transforms from strange to aggressively physical. The tidal stretching is no longer a subtle sensation but a steady, increasing force, as if the very fabric of your being is being drawn out along an invisible line. You are not being ripped apart yet, but the intention of the universe is now clear, a silent, geometric command to lengthen. Meanwhile, the sensory assault from the collapsing sky intensifies into something overwhelming. All the radiation that followed you in, from the faint whisper of the cosmic microwave background to the brilliant light of ancient stars, has been compressed by your furious descent. This light, blue-shifted to extreme, punishing frequencies, now pours upon you from behind as a scorching, blinding glare. It is the accumulated history of the cosmos, transformed into a wall of pure energy and heat, pushing you forward into the dark. If this black hole feeds on a surrounding accretion disk, a new and terrifying spectacle now engulfs your view. That luminous whirlpool of superheated matter, which from afar looked like a distant halo, now wraps completely around the horizon's throat. You are inside the storm. It surrounds you like a tunnel of furious light, a maelstrom of plasma and radiation spinning at relativistic speeds, its inner edge defining the darkness ahead. The roar of this cosmic waterfall would be silent in the vacuum, but space itself may not be. Some theoretical models suggest the violently churning spacetime near the Singularity could generate vibrations, a profound, subsonic rumble felt more in your bones than heard with your ears, the fabric of reality groaning under the strain. The experience is no longer just visual or conceptual. It is a full sensorium crescendo, an engagement of every hypothetical sense. You are stretched by gravity, seared by ancient light, encircled by a whirlpool of fire, and immersed in the resonant hum of bending reality. This is the universe concentrating itself into a single, inescapable point of focus, and you are at its center. The 21st second marks the beginning of a deeper, more conceptual unraveling. As the physical stretching intensifies and the maelstrom of light roars, a quieter, more profound breakdown occurs within the very framework of how events are ordered. This is the loss of simultaneity, the moment the shared concept of now shatters into 1,000 pieces. In our everyday world, if two people synchronize their watches and witness a lightning strike, they can agree on when it happened. They share a common slice of time. Inside the event horizon, this fundamental agreement becomes impossible. Consider two astronauts falling into the same supermassive black hole, but one jumps in a few minutes after the other. For the first astronaut at their personal 25th second, a specific event occurs, perhaps a final systems check reading on their console. For them, that reading and their clock hitting 25 are simultaneous. But for the second astronaut, falling along a different path through this violently curved spacetime, that same event from the first ship might appear to have happened earlier or later, or not even be observable yet. There is no universal clock, no agreed-upon moment that defines the present for everyone inside. It is as if they have fallen into a vast, twisting cave from separate entrances. Each explorer can map their own immediate surroundings, their own personal experience of time, but when they compare notes, their maps of the cave's geometry would bear no coherent relationship to one another. The cave itself seems to rearrange its structure based on the path you took to enter it. This quantum of chaos is not just a mathematical curiosity. It is a direct signal from the universe that the classical, orderly physics we rely on is beginning to fracture at the seams. The reliable stage of space and time, upon which all events were once neatly ordered, is now warping into a labyrinth where cause and effect themselves start to lose their grip. This internal disagreement about the present is the prelude to a far greater mystery, a frontier where our understanding of reality dissolves into pure, untamed speculation. The final minute of personal time is a descent into a realm beyond physics as we know it. For our astronaut, the relentless stretching and the blinding light show continue, but the very stage upon which this drama is playing begins to transform. The curvature of space-time, warped beyond recognition by the black hole's mass, becomes so unimaginably severe that the rules themselves must change. We are approaching a scale so small, it redefines the meaning of small. This is the domain of the Planck length and Planck time, the universe's fundamental units. The Planck length is about 1.6 times 10 to the negative 35 meters. To even attempt to grasp this, consider that an atom is to a planet what a planet is to the observable universe. Now shrink an atom by that same staggering factor again, and you are approaching the Planck scale. It is the smallest distance that has any physical meaning in our current theories. Similarly, Planck time is the interval it would take a photon to travel that tiny distance, about 5.39 times 10 to the negative 44 seconds. It is the tick of a clock so fast, the entire history of our universe since the Big Bang is an eternity spanning some 10 to the 60 Planck ticks. At these scales, the smooth, continuous fabric of spacetime described by Einstein's general relativity can no longer hold. The gentle curves and warps that guide planets and trap light become a violent, churning froth. Think of the surface of the ocean on a calm day viewed from an airplane. It appears as a vast, smooth sheet, but descend to the level of individual water molecules, and that smoothness dissolves into a chaotic dance of discrete particles, constantly colliding and shifting. At the Planck scale, spacetime itself is theorized to behave this way, becoming a seething quantum foam. Here, the very ideas of here and there, before and after, lose their classical certainty. The astronaut's smooth, deterministic plunge toward the singularity begins to dissolve into a haze of probabilities. Their path is no longer a single, inevitable line, but a cloud of possibilities, a quantum superposition of positions and outcomes. The classical notion of a central, infinitely dense point may itself be an illusion, a placeholder for a state of reality our mathematics cannot yet describe. This final minute is not just a journey toward a physical location. It is a journey to the edge of scientific understanding, where our two great pillars of physics, general relativity and quantum mechanics, meet and clash in a storm of pure potential. What lies beyond this frontier is not a destination we can yet map, only a profound and humbling mystery. This final frontier is not a place you can point to on a map. We have arrived at the concept of the singularity, the unknowable end point of this entire journey. In the classical equations of general relativity, the singularity is a mathematical point of infinite density and infinite curvature, a place where the very fabric of spacetime is torn apart. It is where the rules we have been following, the warped geometry and distorted light, finally fail completely. The equations produce nonsensical infinities, a clear sign that our description of reality has reached its limit. But here is the crucial, mind-bending shift. Inside the event horizon, you do not travel to the singularity as if it were a location in space. Because of the extreme warping, the roles of space and time swap. The direction toward the center is no longer a spatial dimension you move through, like walking across a room. It becomes your future. The singularity is not a place you are going, it is a moment you are destined to meet. Every possible path through this distorted realm terminates at that point, making it an inevitable event on your personal timeline, as unavoidable as tomorrow's sunrise. This transforms the experience from a voyage to a fate. You are not falling through space anymore, you are being carried by time itself toward a single, inescapable moment. The philosophical weight of this is immense. According to classical physics, when you meet that moment, all the information that made you, every atom, every memory, every quantum state, is crushed into that infinite point and lost forever. It is the ultimate erasure from the cosmic record. This presents science with one of its greatest puzzles, the black hole information paradox. If information cannot be destroyed, as quantum mechanics insists, but a classical black hole destroys it utterly, then our understanding of reality has a profound contradiction at its heart. This paradox is not a flaw, but a clue. It is a signal that a deeper theory, one that unifies gravity and quantum mechanics, must exist. The singularity, therefore, is less a final answer and more a profound question mark written into the universe, a boundary beyond which our current knowledge cannot see, hinting at truths about reality we have yet to discover. But what if you were not the one falling? Let us shift the frame of view completely to a companion watching from the safety of a distant observation ship. For them, the story of your descent does not end with a silent crossing. It unfolds as a tragedy in super slow motion, stretched across an eternity. As you approach the event horizon, the light carrying your image had to climb out of the black hole's immense gravitational well. Each subsequent photon, emitted from your spacecraft a fraction of a second later, had to fight against an even stronger pull. To your distant friend, this means each signal takes longer and longer to arrive. Your clock, from their perspective, ticks slower with each passing moment. The consequence is both beautiful and heartbreaking. You do not vanish. Instead, you appear to slow down, approaching the event horizon asymptotically. You never quite reach it. You hang there, frozen in the final moment before the crossing, your image reddening and dimming as the light waves are stretched to invisibility. Over an infinite amount of external time, from their point of view, you simply fade from the universe like a ghost. This creates two utterly contradictory, yet equally valid realities. Inside, you experienced a smooth, continuous passage, a journey of seconds and minutes that ended in a plunge toward the unknown. Outside, your companion witnesses a permanent monument to your last moment, a statue of light eternally poised at the brink. This is the observer paradox, and it is not a mistake in the equations. It is a fundamental feature of Einstein's relativity, screaming at us that there is no universal now. The concept of simultaneous events shatters when gravity is this strong. Your reality and your friend's reality, though describing the same person, are no longer reconcilable into a single, shared timeline. The universe permits both narratives to be true within their own frames of reference. This profound disconnect is perhaps the most humbling lesson of the black hole. It tells us that experience is not absolute. What one observer witnesses as a swift and certain fate, another sees as an endless, suspended animation. Both are correct, and the truth lies in the terrifying realization that the universe does not have a single, preferred story to tell. It has many, and they do not always agree. The journey we have just described is not a universal fate. The nature of your final moments depends entirely on the scale of the abyss you approach. The mass of a black hole determines everything, from the size of its event horizon to the very texture of the experience inside it. To understand this, we must contrast two extremes, the stellar mass black hole and the supermassive behemoth. A stellar mass black hole, the collapsed core of a massive star, might contain just a few times the mass of our Sun, compressed into a sphere barely a few dozen kilometers across. Its event horizon is terrifyingly compact, because gravity's strength depends not just on mass but on how closely that mass is packed. The gradient of its pull is unimaginably steep. The difference in gravity between your head and your feet becomes catastrophic long before you even reach the point of no return. For a hypothetical astronaut, the crossing would be a brief, violent end. The process of spaghettification, that gentle stretching we described inside a supermassive giant, would occur with ferocious intensity in the emptiness of space, well outside the event horizon. You would be pulled apart into a stream of atoms by tidal forces far beyond any material's strength to resist. The actual moment of crossing the horizon, if you could even perceive it, would be a final, instantaneous flash in a process of destruction that began minutes or hours earlier. There is no contemplative journey, no slow unfolding of paradoxes, only a swift and physical dissolution. Now, shift your perspective to the supermassive black hole at the heart of our own galaxy, Sagittarius, a star. This monster contains millions, even billions, of times the mass of our Sun. That immense mass is spread over a correspondingly immense volume. Its event horizon is not a few kilometers across, but millions of kilometers wide, a sphere so vast you could fit our entire solar system inside it with room to spare. This scale changes everything. The gravitational pull at the event horizon of Sagittarius, a star, is still strong enough to trap light, but because that horizon is so far from the central point of extreme curvature, the tidal gradient is remarkably mild. You could cross that boundary physically intact. The difference in pull between your head and your feet at the moment of crossing would be negligible, perhaps no more than the feeling of a gentle tug. It is this specific, almost placid entry that allows for the analytical, second-by-second journey we have been exploring. The profound warping of time, the reordering of space, the visual paradoxes, all of these are experiences granted only by the vast, deep gravity well of a supermassive giant. This comparison is not just academic, it is fundamental. It tells us that black holes are not a single phenomenon with a uniform effect. They are a category, ranging from the small and violently destructive to the colossal and strangely permissive. Your story, should you ever find yourself on such a fatal trajectory, is written not by the fact of the black hole itself, but by the sheer astronomical scale of the one you choose or are chosen by to confront. But the smooth, geometric descent described by classical physics may not be the final word. Our journey through the event horizon, second by agonizing second, was painted with the brush of Einstein's general relativity. It is a powerful and elegant picture, but it is incomplete. It ignores the other great pillar of modern physics, quantum mechanics, and when we bring quantum rules into this blackest of places, the entire story can change in radical, even violent ways. This is the frontier of theoretical physics, where the event horizon transforms from a silent mathematical boundary into a zone of fiery paradox and ghostly possibility. One of the most startling ideas to emerge from this clash of theories is the black hole firewall hypothesis. Imagine for a moment that the event horizon is not an empty gateway. Instead, picture it as a seething wall of unimaginably high energy, a literal curtain of fire made from the most fundamental particles. According to this radical proposal, anything attempting to cross would not experience a gentle geometric transition, but would instead be instantly and completely incinerated. This firewall is not born from malice, but from a desperate attempt to preserve one of quantum mechanics' most sacred principles, the law that information cannot be destroyed. The paradox is this: from the outside, information about what fell in seems to be smeared and lost as Hawking radiation slowly evaporates the black hole. But from the inside, according to relativity, that information should just sail smoothly through the horizon intact. To resolve this, some physicists suggest a drastic rewrite. The smooth interior must be sacrificed to save the information law. The horizon becomes a destructive filter, a cosmic shredder that ensures no information ever actually enters the black hole's interior in the first place. It is a brutal solution, turning the point of no return into a point of immediate termination. Yet not all quantum corrections lead to such a fiery end. There exists another, far more elusive possibility woven into the fabric of quantum theory itself: tunneling. In the subatomic world, particles can perform seemingly impossible feats. An electron confined inside a box, according to classical physics, should never be found outside it. But quantum mechanics allows for a tiny, probabilistic chance that the electron will simply appear on the other side of the wall, as if it found a secret, ghostly passage. This is quantum tunneling, and it underpins the nuclear fusion that powers our sun. If we apply this bizarre logic to the extreme geometry of a black hole, a tantalizing, almost magical idea emerges. Perhaps the immense curvature of spacetime at the horizon creates not a wall, but a probabilistic labyrinth. For an object falling in, the overwhelming likelihood is that it continues its classical plunge toward the singularity. But there exists a probability so vanishingly small it defies imagination, a chance that the object, or perhaps some scrambled quantum information of it, could tunnel through the warped spacetime and reappear somewhere else entirely. This would not be a tunnel in space you travel through, but a sudden, discontinuous jump from one state of existence to another, a cosmic lottery with odds so astronomical they might as well be zero, yet a chance that is mathematically not quite nothing. These two ideas, the destructive firewall and the ghostly tunnel, represent opposite poles in a fierce and ongoing debate. They show us that the event horizon is not a settled fact, but a living question. Our understanding of this boundary is still evolving, filled with active mystery and profound disagreement. The classical journey we mapped may be just one possible story in a multiverse of potential fates, reminding us that at the edge of known physics, certainty dissolves, and all we are left with are possibilities waiting to be discovered. The paradoxical nature of the crossing, with its frozen observers and swapped realities, finds its true home not in philosophy, but in mathematics. To understand why the event horizon rewrites the rules so completely, we need to look at the language the universe uses to describe itself, the geometry of spacetime. At the heart of this is a beautiful and powerful concept, the geodesic. In the flat, calm spacetime of our everyday world, the straightest possible line between 2 points is simply a straight line. But place that line in a curved landscape like the surface of the Earth. The straightest path between New York and London is not a straight line tunneling through the planet. It is a gentle arc following the curve of the Earth, a great circle route. This is a geodesic, the natural, unpowered path an object follows through curved geometry. Our astronaut, once their engines cut out, is not steering. They are following a geodesic through the profoundly warped spacetime surrounding the black hole. Their entire fate is written into the curvature of that invisible landscape. We can visualize this dramatic curvature with a remarkable tool, the Penrose diagram. Think of it as a cosmic map that compresses infinite distances and times into a finite, understandable picture. On this map, the path of any object through spacetime is drawn as a world line. Far from the black hole, these world lines can point in any direction, representing freedom of motion. But as they approach the event horizon, drawn on the diagram as a 45-degree line, something stunning happens. All world lines, regardless of their original angle, bend and turn until they are pointing relentlessly inward, parallel to the horizon. The map visually confirms the inescapable truth. Once that boundary is crossed, every possible future leads deeper into the interior. The mathematical engine behind this map is the Schwarzschild metric, an equation derived from Einstein's field equations that describes the exact shape of spacetime around a simple, non-rotating black hole. This equation has terms for how we measure intervals of space and time. Outside the event horizon, these terms behave as we expect, keeping space and time as distinct, familiar concepts. But if you could plug in the exact coordinates of the horizon itself, a profound shift occurs within the math. The terms associated with radial distance and time effectively swap their signs. What was a coordinate measuring space suddenly behaves like a coordinate measuring time, and vice versa. This is not a quirky math trick. It is the universe's own ledger, recording the moment when moving forward in space becomes synonymous with moving forward in time. The radial direction toward the singularity ceases to be a place you can choose to visit or avoid. It becomes your future, an inevitable moment on your personal clock. This mathematical lens transforms the strange sensory journey into a clear, geometric certainty. The blinding light, the stretching force, the loss of simultaneity, all of these are not random horrors, but inevitable consequences of traveling along a geodesic in a spacetime where the very definitions of here and there have been fundamentally rewritten by the silent, relentless logic of the metric. The journey to this profound understanding did not begin with supercomputers or space telescopes, but with a thought experiment in the late 1700s. A British natural philosopher named John Michell, using Newton's laws of gravity and the new understanding of light as a particle, performed a stunning calculation. He reasoned that if a star were massive and dense enough, its gravitational pull would be so strong that not even light could escape. He called these objects dark stars, and while his concept was based on a different physics, it was the first intellectual spark, a prediction of invisible cosmic traps made over a century before Einstein rewrote the rules of gravity. The true mathematical birth of the black hole came from a battlefield. In 1916, while serving in the German army during the First World War, the physicist and astronomer Carl Schwarzschild found a solution to Albert Einstein's brand new and notoriously complex field equations of general relativity. His solution described the curvature of spacetime around a perfectly spherical, non-rotating mass. Within his equations lay a strange term, a radius where the mathematics broke down into infinity. This was the first precise description of what we now call the event horizon, though its full, terrifying implications would take decades to unravel. For years, this Schwarzschild radius was seen as a mathematical curiosity, an artifact unlikely to exist in the real universe. The idea that stars could collapse into such a state was considered absurd. That changed because of a young physicist on a ship from India to England. Subramanian Chandrasekhar, just 19 years old, calculated that a white dwarf star, the dense remnant of a sun-like star, could not exist above a certain mass limit. If a dying star's core exceeded this Chandrasekhar limit, about 1.4 times the mass of our Sun, no known force could prevent its catastrophic collapse. The established scientific community, led by Sir Arthur Eddington, resisted the idea fiercely, but the math was sound. The door to gravitational collapse had been nudged open. The final push came in 1939 when Robert Oppenheimer and his student Hartland Snyder took Chandrasekhar's work to its logical, dramatic conclusion. They published a paper describing how a sufficiently massive star, once its nuclear fuel was spent, would undergo relentless gravitational collapse, crushing itself out of contact with the rest of the universe. Their work painted a stark picture, but it was still seen as a theoretical extreme. The modern understanding of the event horizon as a physical, crossable boundary, rather than a mathematical singularity to be avoided, was cemented by the physicist David Finkelstein in 1958. He showed that the Schwarzschild radius was not a true physical singularity, but a coordinate singularity, a place where our human-chosen labels for space and time failed, not the laws of physics themselves. This was the critical insight that transformed the black hole from a mathematical oddity into a plausible astrophysical object, a place you could, in theory, approach and even enter. The story then took its most unexpected turn thanks to Stephen Hawking. In the early 1970s, Hawking applied the strange rules of quantum mechanics to the curved space just outside the event horizon. He discovered that black holes are not completely black. Due to quantum fluctuations, they can slowly emit a faint glow of particles, now known as Hawking radiation. This revelation was revolutionary, suggesting that black holes have a temperature and can eventually evaporate over astronomical timescales. It also created the famous information paradox, a puzzle that continues to drive theoretical physics today. This entire intellectual journey, from Mitchell's dark stars to Hawking's glowing horizons, is a testament to the power of human curiosity. Each thinker, building on the work of those before them, peeled back another layer of this cosmic mystery. Their collective struggle with mathematics and imagination is what allows us to now sit back and envision, with such vivid, second-by-second detail, the ultimate voyage to the edge of reality. The journey across the event horizon, for all its personal finality, is just one small transaction in a vast cosmic economy. To grasp its true significance, we must pull our view back, far beyond the fate of a single astronaut, to the scale of entire galaxies. At the heart of most, if not all, large galaxies like our own Milky Way, sits a supermassive black hole. These are not passive sinkholes, but dynamic engines whose activity, powered by the very matter crossing their event horizons, shapes the destiny of billions of stars. This is where the personal crossing meets the galactic narrative. Every bit of gas, dust, or even an entire star that spirals past the point of no return releases a staggering amount of energy before it vanishes. As matter is accelerated and compressed in the furious accretion disk, it heats to millions of degrees, glowing brilliantly across the electromagnetic spectrum, and often launching colossal jets of particles at near light speed. This outpouring of energy acts as a cosmic regulator. It can heat surrounding gas clouds so violently that it prevents them from cooling and collapsing to form new stars, effectively putting a brake on star birth in the galaxy's central regions. In more extreme cases, these powerful jets can blast gas entirely out of the galaxy, stripping away the raw material for future generations of stars and planets. This process, known as black hole feedback, creates a delicate balance. The black hole feeds, it grows, and in doing so, it unleashes energy that limits its own future food supply and dictates the pace of galactic evolution. The event horizon is the gate through which the fuel must pass to power this entire cycle. By studying the physics at this boundary, the way matter behaves in its final moments, astrophysicists gain crucial insights into the efficiency of this engine. How much energy is radiated away versus swallowed forever? How does the spin of the black hole affect the power of its jets? The answers to these questions, rooted in the dynamics of the horizon, help explain why some galaxies are ablaze with star formation while others are quiet, aging stellar metropolises. So, analyzing that fateful crossing is far more than a terrifying thought experiment. It is a fundamental key to understanding the life cycle of galaxies. The silent, invisible boundary that seals one fate simultaneously governs the birth and death of stars on a scale we can scarcely comprehend, making the event horizon not just a prison of space-time, but a cornerstone of cosmic structure. This profound understanding, however, rests on a foundation of mathematics and imagination, not direct observation. We cannot simply build a spacecraft and send a probe to report back from the other side. The obstacles are not merely engineering challenges, they are absolute barriers written into the laws of physics. The first is sheer, staggering distance. The nearest known black hole, let alone a suitable supermassive one, is thousands of light-years away. A journey there with any conceivable technology would take tens of thousands of years, a timescale that dwarfs all of recorded human history. Even if we could traverse such a void, the probe itself would face annihilation. To survive the crossing of a supermassive black hole's event horizon intact, as our narrative described, the craft must be enormous to withstand the tidal stretching, and shielded beyond any known material to endure the blistering radiation from the compressed accretion disk and the blue-shifted cosmic background. We are speaking of a vessel more akin to a fictional starship than any probe we have ever designed. But these are almost trivial concerns compared to the ultimate, insurmountable wall, the communication problem. This is the heart of the matter. Any signal, whether a simple radio ping or a complex data stream, is carried by photons or some other particle moving at or below the speed of light. And as we have established, nothing, not even light, can escape from inside the event horizon. The moment the probe crosses that boundary, its transmission antenna, no matter how powerful, is pointing into a prison from which its signal can never climb out. The probe could collect terabytes of data every second, but that information is now locked away with it forever, falling toward the singularity. We would be launching a diary into a cosmic vault and throwing away the key. Some highly speculative theories in cosmology have proposed potential loopholes, though none are remotely within our reach. Concepts like stable cosmic strings, hypothetical one-dimensional defects in spacetime, or traversable wormholes suggest the possibility of shortcuts through the universe. In theory, such a structure might connect the interior of a black hole to another point in spacetime, offering a way out. But these ideas remain purely mathematical possibilities. No evidence for cosmic strings or usable wormholes exists, and the energies required to stabilize or create them are beyond anything we can envision harnessing. For all practical purposes, with the technology we possess or can reasonably foresee, a direct observational mission to the event horizon is impossible. This acknowledgement of our limits, however, is not a defeat. It is what makes the theoretical journey so powerful. By rigorously following the equations of general relativity, we can simulate the crossing in supercomputers and in our minds, exploring the consequences of our theories to their extreme. Each paradox we uncover, like the information paradox or the firewall hypothesis, is not a sign of failure, but a bright flare illuminating the boundaries of our current knowledge. They show us exactly where our understanding of gravity and quantum mechanics fractures, guiding physicists toward a deeper, more complete theory of reality. The fact that we cannot go there physically makes the intellectual journey all the more essential, for it is by staring into this absolute abyss with the tools of mathematics and logic that we discover the most profound truths about the universe we actually inhabit. Yet we are not left in total darkness. While a physical voyage remains impossible, we have crafted a different kind of vessel, one made not of metal but of mathematics and light. Supercomputers have become our virtual spacecraft, allowing us to simulate the plunge across the event horizon with breathtaking precision. These are not simple animations, they are full-scale physics engines that solve the complex equations of general relativity in real time, calculating how every single photon of light would bend and twist as it travels through the warped spacetime around a black hole. This process, called relativistic ray tracing, is akin to reverse engineering the view. Scientists start with a model of the black hole and its glowing accretion disk, then fire millions of virtual light rays from the perspective of a hypothetical camera. They trace each ray backward along its curved path through the simulated gravity well, noting where it originated, whether from the far side of the disk, a distant star, or even multiple times from the same hot spot of gas as light loops around the black hole. The result is a visualization that is both scientifically rigorous and visually stunning. We see the accretion disk not as a flat plate, but as a warped, luminous halo that bends over and under the black hole's shadow. We witness the phenomenon of multiple imaging, where a single bright knot in the disk appears as a fractured ring of echoes, its light having taken different paths around the gravitational trap. These simulations transform the abstract tensor equations of Einstein into a visceral, navigable experience. Landmark projects like those from NASA's Goddard Space Flight Center have given us the iconic view from the brink, showing the sky pinched into a ring and the universe's history playing out in fast forward. They allow us to sit in the cockpit of that doomed spacecraft and finally see what the equations have been telling us all along. But the ultimate validation of this virtual exploration came from an extraordinary feat of observational astronomy. The Event Horizon Telescope collaboration did not simulate a black hole, it photographed one. By linking radio telescopes across the globe to create an Earth-sized virtual dish, the collaboration captured the first direct image of the supermassive black hole at the heart of galaxy Messier 87. That now famous orange ring of light is not the event horizon itself, which is invisible, but the shadow it casts against the backdrop of its superheated accretion disk. The light from the disk behind the black hole is bent so severely around it that it forms a bright ring, outlining the dark silhouette of the point of no return. This image was a triumph of simulation as well as observation. To interpret the faint radio signals, scientists had to compare them against millions of possible simulated images, each based on different assumptions about the black hole's spin, the disk's orientation, and the physics of the hot plasma. The fact that the predictions from general relativistic simulations matched the actual photograph so perfectly was a monumental confirmation of Einstein's century-old theory in the most extreme environment imaginable. Together, supercomputer simulations and telescopic images act as our windows into the unseeable. They bridge the gap between the cold certainty of mathematics and the human need to witness, to visualize, and to comprehend. They tell us that while we may never send a probe into that abyss, we have already sent our curiosity, and it has returned with a picture, a map, and a profound new understanding of the dark hearts that shape our cosmos. This absolute geometry of the interior forces us to confront a haunting philosophical idea. If every possible path leads to one inevitable moment, have we discovered the ultimate expression of fate? The black hole's interior presents a universe stripped of choice, a cosmic corridor where the concept of free will collides with the deterministic map of general relativity. Outside, in the broad universe, your future is a branching tree of possibilities. You could turn left or right, accelerate or brake, your decisions weaving a unique path through spacetime. But once across that invisible boundary, the tree is replaced by a single, narrowing tunnel. All branches are pruned away. Your trajectory is no longer something you influence. It is a geometric fact as predetermined as the orbit of a planet. This is not a matter of insufficient engine power. It is a rewriting of the very structure of possibility. The universe inside a black hole operates with a chilling, perfect determinism. It compels us to ask if the laws of physics can create a domain where choice is geometrically erased. What does that imply about the nature of choice elsewhere? Are we, in our daily lives, truly navigating a garden of forking paths, or are we, like the astronaut in the final plunge, simply following the deepest grooves in the curvature of a cosmic landscape we cannot perceive? The event horizon magnifies this question to a terrifying scale, holding up a mirror to our deepest uncertainties about agency and destiny in a relativistic cosmos. Yet, this deterministic perfection creates its own profound contradiction, one that threatens to unravel our understanding of reality at its most fundamental level. This is the black hole information paradox. In the classical picture, every atom, every memory, every shred of data that makes up the astronaut and their ship is irretrievably crushed at the singularity. That information is erased from the universe forever, but quantum mechanics, the rulebook for the very small, contains a sacred, unwavering law: information cannot be destroyed. It can be scrambled, hidden, or transformed, but it must persist. If a book is burned, the ash and smoke still contain, in principle, the information needed to reconstruct every word. The black hole, according to classical relativity, does not burn the book, it annihilates it from existence. Stephen Hawking's own work on radiation seemed to suggest that when a black hole finally evaporates, it leaves behind only a featureless haze of particles with no record of what fell in. This presents science with an either-or dilemma of stunning magnitude. Either our cherished principle of quantum information is wrong, or our beautiful geometric picture of the smooth event horizon and deterministic interior is incomplete. The existence of this paradox is not a failure of physics, but a brilliant beacon. It is the universe's way of telling us that our two most successful theories, general relativity and quantum mechanics, cannot both be the final word in this extreme realm. Their clash at the event horizon is a direct signal that a deeper, unifying framework is required, a theory of quantum gravity. This sought-after theory would describe how spacetime itself behaves at the quantum level, explaining the fate of information and the true nature of the singularity. The event horizon, therefore, transforms from a mere astronomical phenomenon into the ultimate philosophical and scientific laboratory. It is a natural experiment constructed by the cosmos itself, where the deepest questions about causality, the preservation of history, and the very fabric of reality are tested under conditions of unimaginable extremity. By staring into this abyss and grappling with its paradoxes, we are not just studying black holes, we are probing the foundational rules of existence, seeking the hidden language that writes both the deterministic curve of a geodesic and the probabilistic dance of a quantum particle. The profound questions raised by the black hole's interior have not remained locked within scientific journals. They have ignited the collective imagination, finding powerful expression in our stories and films. This cultural journey often begins with a single, terrifyingly beautiful image, a swirling vortex of darkness that promises both annihilation and revelation. In the realm of fiction, the black hole serves as the ultimate plot device, a doorway to the unknown that forces characters to confront cosmic-scale dilemmas. For decades, many portrayals leaned into pure fantasy, depicting black holes as literal tunnels to other dimensions or malevolent cosmic monsters. These stories use the concept as a backdrop for adventure, focusing on the fantastical escape rather than the scientific reality. Yet, this began to change as our actual understanding deepened. leading to a new era of scientifically informed storytelling. The landmark film Interstellar stands as a pivotal moment in this evolution. Director Christopher Nolan collaborated closely with Nobel laureate physicist Kip Thorne, who served as both scientific consultant and executive producer. Thorne's equations directly generated the visual effects for the film's supermassive black hole Gargantua. The result was not a guess, but a computational visualization of how light would truly bend around a rapidly spinning singularity. The stunning, luminous accretion disk wrapping over the top of the black hole's shadow was a revelation to audiences, a piece of art born from raw general relativity. The film's heart-wrenching depiction of time dilation on the water world, where hours near Gargantua equal decades back on Earth, brought a profound scientific consequence to life as visceral human drama. This commitment to accuracy did not limit the story, it elevated it, grounding its themes of love, sacrifice, and connection across time and space in a framework of authentic physics. The black hole became more than a setting, it became a character embodying the relentless laws of the cosmos. Other narratives explored different, yet equally resonant, aspects of the mystery. Stories often use the event horizon as a metaphor for the point of no return in human experience, a moment of irreversible commitment or sacrifice. The themes of information loss and causality breaking down naturally lend themselves to plots involving time loops, paradoxical communication, and altered realities. When a character sends a message from beyond the horizon, or when time itself fractures near the singularity, these plots are wrestling with the same paradoxes that keep theoretical physicists up at night. This cultural reflection reveals a deep, shared fascination. The black hole, and specifically the moment of crossing its threshold, taps into fundamental human curiosities and fears. It represents the ultimate unknown, the final journey, the sacrifice for greater knowledge, and the haunting possibility of lost time and lost connections. By transforming complex tensor equations into narratives of love and survival, filmmakers and writers perform a vital translation. They bridge the gap between the abstract mathematics of curved spacetime and the universal human experience, allowing the public to feel the weight of these cosmic truths. The event horizon, therefore, exists in two parallel realms. It is a precise mathematical boundary studied with telescopes and supercomputers, and it is a powerful symbol in our collective psyche, a modern myth born from science that continues to shape how we envision our place in a vast and mysterious universe. These profound questions will soon be tested by a new generation of cosmic observatories. While we cannot send a probe across the event horizon, we are building instruments that will listen to the very fabric of spacetime shudder as black holes collide. The future of black hole science lies not in crossing the boundary, but in decoding the intricate vibrations it creates in the universe. The upcoming Laser Interferometer Space Antenna, known as LISA, is a mission of breathtaking ambition. Instead of a single telescope, it will be a constellation of 3 spacecraft, flying in a perfect triangular formation millions of kilometers apart, trailing the Earth in its orbit around the Sun. Their sole purpose is to detect the faintest ripples in spacetime, gravitational waves, at frequencies that ground-based detectors cannot hear. This will open a window onto the mergers of the universe's most colossal objects, supermassive black holes. When 2 of these giants in the hearts of merging galaxies finally spiral together, they will create a gravitational tsunami that LISA is designed to capture from across the cosmos. The signal will tell us not just about their masses and spins, but about the very nature of the event horizons as they violently stretch and merge. It is the closest we will come to witnessing the dynamics of that one-way membrane itself. Alongside these gravitational wave observatories, a new fleet of advanced X-ray telescopes is being designed. These instruments will peer at the final moments of matter just outside the point of no return, studying the inner edge of accretion disks with razor-sharp precision. They will measure how spacetime is dragged around a spinning black hole, map magnetic fields strong enough to tear atoms apart, and watch how superheated gas winks out of existence as it crosses the threshold. But perhaps the most subtle and revealing signal of all is what physicists call the ring-down. After two black holes collide and merge, the single, new black hole that forms is not perfectly smooth and silent. It is misshapen, wobbling like a struck bell, and it must settle down into a quiet, symmetrical state. This settling process emits a specific set of gravitational wave frequencies, known as quasi-normal modes. These are the unique ringing tones of spacetime itself, the characteristic sound of an event horizon stabilizing. By analyzing this ring-down with exquisite precision, scientists can perform a remarkable test. The specific frequencies and how quickly they fade away are direct signatures of the black hole's properties, dictated by general relativity. Any deviation from Einstein's predictions in this ringing could be a smoking gun for new physics, perhaps a hint of what lies beyond the classical horizon, or evidence for exotic structures like wormholes. These future observations represent a fundamental shift. We are moving from taking still photographs of black hole shadows to making detailed movies of their dynamics and recording the symphony of their collisions. Each gravitational wave chirp and every X-ray flicker from the precipice is a piece of data that constrains the millions of possible theoretical models. While we will never see the crossing directly, these missions will probe the extreme gravity around the event horizon with such fidelity that they will either confirm our relativistic picture in stunning detail or force us to rewrite the textbooks. The horizon remains an impassable wall, but we are learning to listen intently to the echoes it creates, echoes that may finally reveal the true nature of the universe's most absolute boundary. But what if the entire visceral journey we just described is not what is truly happening? There exists a theoretical concept so radical it reimagines the very nature of that descent. This is the holographic principle, and it proposes that the astronaut's entire three-dimensional experience inside the black hole might be nothing more than a magnificent illusion. The idea begins with a startling calculation about information. In the 1970s, physicist Jacob Bekenstein, building on Stephen Hawking's work, realized that a black hole's entropy, a measure of its hidden information content, is not proportional to its volume as you might expect. Instead, it is proportional to the area of its event horizon. This was a profound clue. In our everyday world, the information needed to describe a room, every dust mote, every air molecule, scales with the room's three-dimensional volume. But for a black hole, the ultimate container, the maximum information it can hold is painted onto its two-dimensional surface. This led theorists like Gerard T. Hooft and Leonard Susskind to a breathtaking proposition. Perhaps the entire interior of the black hole, with its warped spacetime and falling astronaut, is like a hologram. A hologram you might see on a credit card is a flat, two-dimensional surface that, when illuminated with laser light, projects a stunningly realistic three-dimensional image. The holographic principle suggests the universe might operate on a similar, though far more fundamental, level. The true, fundamental description of reality for everything within the black hole's volume could be entirely encoded on its event horizon, written in unimaginably tiny quantum bits or qubits on that spherical surface. The astronaut's sensation of falling, the stretching, the distorted starlight, all of it would be a three-dimensional projection from that two-dimensional data. In this view, crossing the event horizon is not about entering a new volume of space. It is about your information being transcribed, pixel by quantum pixel, onto the most intricate cosmic hard drive imaginable. This principle, emerging from the depths of string theory, offers a compelling escape from the information paradox. The information about the astronaut is never actually destroyed inside a singularity because it never truly enters a three-dimensional interior. It is stored, scrambled but preserved, on the horizon's surface and could, in theory, be slowly radiated back out over eons via Hawking radiation. The implications ripple far beyond black holes, hinting that our entire three-dimensional universe might itself be a holographic projection from a distant two-dimensional boundary. It is a concept that challenges our most basic assumptions about reality, suggesting that depth, solidity, and the very space we move through could be the universe's most convincing and elegant illusion. The holographic principle, with its vision of reality as a projected illusion, brings us to a quiet but profound crossroads. We have charted the physics of the crossing, but now we must ask a different kind of question. What does it mean for us as conscious beings to live in a universe that contains such absolute and destructive boundaries? The black hole is not just an astronomical object, it is a philosophical mirror. The relentless geometric inevitability of the fall inside the event horizon, where all paths converge on a single moment, echoes themes we wrestle with in our own lives. Our personal timelines, too, are one-way journeys. We speak of points of no return, of moments that change a life's trajectory forever, of the quiet, inescapable forward march of time. The black hole takes this human experience and engraves it into the fabric of the cosmos, presenting us with a cosmic metaphor for fate, written in the language of curved spacetime. It forces us to confront the idea that the universe itself can architect domains where freedom is not just limited, but geometrically erased. This realization can feel deeply humbling, even unsettling. We are shown a scale of existence where our stories, our struggles, and our very civilizations are less than whispers against the silent roar of gravity. In the face of such an abyss, it would be easy to see only futility. Yet there is another, far more powerful response, and it is written in the very history of how we came to understand these objects. Consider the courage embedded in scientific inquiry itself. For over a century, physicists have stared into this mathematical and conceptual abyss. They did not look away from the terrifying implications of infinite density or information loss. Instead, they leaned in, using the tools of logic and mathematics to map the unseeable. This is not a cold, detached process. It is an act of profound bravery and curiosity, a refusal to let the universe have secrets too dark to examine. Each paradox uncovered, from the information dilemma to the firewall, is not a sign of failure, but a testament to the rigor of the human mind, a mind that insists on asking what happens next, even when next leads to a place from which there is no return. This pursuit does the opposite of diminishing us. It showcases our most extraordinary trait, the ability to decipher the cosmos's deepest rules from a safe distance of light years and thought experiments. We take the faintest whispers of radiation, the subtle wobble of stars, and the precise ring of colliding space-time, and from that, we construct an understanding of realms forever beyond our physical reach. The study of black holes, therefore, delivers a dual lesson. It grounds us, reminding us of our physical fragility and the vast, unknown depths of reality. But it also elevates us, revealing that through patience, creativity, and relentless questioning, we can extend our comprehension to the very edge of what is possible. We may never cross that horizon, but in seeking to understand it, we have expanded the horizons of our own understanding in ways that forever change how we see our place in the grand and mysterious story of everything. So we have stood together at the precipice and followed the path all the way down. We began with a silent mathematical transition, a crossing that felt like nothing at all within the cockpit, a simple rearrangement of future possibilities into a single, narrowing corridor. We witnessed the visual spectacle of the cosmos collapsing into a ring of light, a fast-forward film of cosmic history playing on the walls of a prison. We felt the awakening of tidal forces, that gentle, inexorable stretch as the universe began to sculpt matter with geometric certainty. we navigated the conceptual unraveling where space and time swapped roles, where the singularity transformed from a place into an inevitable moment, and where the shared concept of now shattered into irreconcilable fragments. We even ventured to the quantum edge, where space-time itself dissolves into a seething foam of probabilities. This entire journey, second by second, reveals the event horizon for what it truly is, not a wall of rock or fire, but a threshold of transformation. It is the point where the familiar physics of our universe, the reliable stage of space and time, begins to fold in upon itself. Here, gravity ceases to be merely a force that pulls on objects. It becomes the architect of reality, warping the very definitions of here and there, before and after. The key takeaway is not just the destruction, but the metamorphosis, the crossing marks where our classical, intuitive understanding of the cosmos reaches its absolute limit and begins to break down. The paradoxes we encountered, from the frozen observer to the lost information, are not errors. They are flashing warning signs on the road of human knowledge. They tell us with perfect clarity exactly where our two most successful descriptions of reality, Einstein's grand geometry of spacetime and the bizarre rules of the quantum world, collide and contradict. This makes the black hole's event horizon far more than a cosmic curiosity. It is the universe's own ultimate laboratory, a natural experiment operating at energies and densities impossible to recreate, posing the most profound questions we can ask. The synthesis of this journey, therefore, connects a deeply personal thought experiment, the fate of a single astronaut, to humanity's grandest intellectual quest. By mapping the descent into the abyss, we are not merely telling a story of an ending. We are charting the very frontier where the next great breakthrough in fundamental science must occur. The struggle to understand what truly happens at that boundary, to resolve its screaming paradoxes, is the direct path toward a deeper theory, one that might finally unite gravity and quantum mechanics into a single, coherent framework, a theory of everything. In seeking to comprehend the point where physics transforms, we are ultimately seeking to comprehend the foundational language of the universe itself. Our shared descent into that absolute darkness has reached its end. We began with a silent line in the geometry of the cosmos and followed its consequences into a realm where light bends into a ring, where time becomes a direction, and where the very fabric of reality is stretched to its breaking point. This second-by-second analysis reveals the black hole not as a simple pit, but as a cosmic transformer. It is a place where the universe takes all the rules we know and warps them into new, terrifyingly beautiful shapes, teaching us that space and time are not a fixed stage, but a dynamic, malleable substance. The true value of this journey lies not in the destination, which remains shrouded in quantum mystery, but in the profound questions the crossing forces us to ask. Every paradox, from the frozen observer to the lost information, is a signpost pointing toward the next great frontier in human understanding. These objects are nature's ultimate experiments, pressing our theories of the very large and the very small into a confrontation from which a deeper truth must emerge. So let this exploration stand as a testament. It is a testament to the universe's capacity for infinite mystery, and to the human mind's relentless courage to map even the most inescapable corners of existence. Our curiosity is the one force that can, in a way, look beyond the horizon. If this journey has reshaped your view of the cosmos, pass that perspective forward. Share this video with someone who wonders about the edges of reality. Subscribe for more voyages into the unknown, and tell us below, what part of this plunge into the abyss left you most in awe, or perhaps most thoughtfully unsettled?